month later in development, all of these classical markers are present, and these neurons still serve the same purpose. So we think we have a window into this earlier stage of development than many people get to look at. And then the other interesting idea that we think is that these neurons acquire their different identities according to their... The electrophysiology in that last set of experiments, and again, thanks to the NIH and for funding, and to you for being here. Other questions? If you have questions, I can answer them either now or at the reception. All right, Dr. Lee says, let's move to the reception.
Well, thanks, Dr. Holly Klein for the wonderful lecture. So there's a reception in the library, and you can talk to Dr. Klein.
Good afternoon. Welcome everybody to the Winston Junior Lecture. I'm John Morse, the Director of the National Institute of General Medical Sciences. I've been asked to remind you that immediately following this lecture, there will be an FAES-sponsored reception in the library. We thank FAES for providing the funds for the cookies and refreshments that will be there. Let me start by telling you fluctuations in the amount of metal ions inside of cells influences key cellular decisions such as gene expression. A variety of approaches, Dr. O'Halloran has uncovered new types of proteins that bind metal ions and has tied their function to a number of disease processes. He began his work as an NRSA-funded postdoc at MIT with Chris Walsh, where he identified the earliest examples of cellular receptors for metal ions that regulate gene expression. About a decade later, he discovered and characterized a second class of metal receptors that govern the flow of metal into and out of cells. These discoveries have since led to novel metal-based anti-cancer compounds, some of which are currently in clinical trials. More recently, Dr. O'Halloran and his colleagues have discovered that fluctuations in metal ion concentration control fundamental developmental decisions in bacteria and also in disease-causing parasites. His team has also demonstrated an important role for fluctuations in intracellular zinc in the fertilization of mammalian eggs. I'm very pleased and proud to be able to say that NIGMS has supported Dr. O'Halloran's research since he joined the faculty at Northwestern in 1986. So now, I'd like to introduce Dr. O'Halloran and his talk entitled Elements of Health and Disease, Inorganic Fluxes and Metal Receptors that Control Cell-Based Decisions. Thank you very much, Dr.
It's a great honor to be here today and to tell all the footsteps of Dr. Seddon as well as the previous lectures in the series. And really excited to tell you about some of the discoveries that have come over the years from our laboratory. And I'm going to take a very kind of classic view of the periodic table, and I want you to realize there are many examples on top of what I'm going to highlight, but I'm going to try to run through a series of arguments that keep expanding the question of how does nature make decisions, how does it use the inorganic components of the cell to make those decisions. So inorganic chemistry, I feel, is poised now to really make major contributions in understanding processes such as proliferation, apoptosis, or programmatic cell death, the decisions to go to a senescent state or to be stem-like and be bird. So fluctuations in metal ions, I believe this is one of the areas in the future that we're going to see a lot of work. I'm not going to talk about those things today. I'm going to talk about some of the fundamental background, the way we started to change our thinking about how elements of the periodic table are used in living systems. system. After all, the word inorganic really stems from the Latin word for not living, and so inorganic molecules should in fact not be playing major roles in biology, but I think as many of you realize that this definition is certainly not so useful, and in fact has held us back for many years in thinking more broadly about the elements of life. I'm going to ask you to think with me and imagine how to look and peer into a cell and figure out where these different metal ions are. And in fact, many of them have about the same kind of charge radius ratio. They're small specks compared to the larger biopolymers. So how can we follow their movements in the cell and then understand how they might play a role in making the cellular decisions? And then ultimately, our interest is to take and translate these discoveries and apply them to really relieving human suffering and improving health. And while that's not the primary focus of my lecture today, I do have vignettes that just show how ideas emerging from basic science research can really transform the trajectory as we think about diseases. So we have to go back to general chemistry, to Chemistry 101, and this is really our Rosetta Stone in nature. The periodic table has such an extraordinary amount of information and relative cross-correlations and phenomenon in chemical behavior. But I wanted to point out to you that life is using a good part of the top part of the periodic table, but not so much of the heavier elements that reside below. And that's pretty much partly because of the abundance in the crust. The smaller, the lighter weight the element, the more that we find in the universe. What I've shown here are elements that we know that should be consumed as part of our diet, and not advocating that you go out and take mineral supplements for the most part. All living systems use most of these metals, and since almost all the food you eat was once living, you're getting a distribution of metals that you need for the most part. If you have a genetic allele that causes you to absorb less or more of one metal, then there needs to be some management. And that's the discovery work that needs to continue to go on. We only know a handful of those types of disorders. So I'm going to talk today particularly about zinc. I'm going to tell you about some of the insights we've gleaned from our working on copper. Much of our work was inspired by the great biology of iron diseases, but I'm really going to focus on those three. I will point out that we're going to start talking about the difference in the chemistry of this part of the periodic table, of this part, and this part, so your general chemistry lesson is not yet over. So these are the kind of fundamental questions I want to run through in fairly quick order. They're kind of a list that you might have if you're asking, well, if metals and elements have to be acquired by cells. These are some of the questions you'd want to know. Are these really trace substances, as many of the textbooks will define zinc, copper, and iron as not being very much in the body? And, okay, so if that's true, how much is there per cell, and is that trace concept really useful? Then the question is, do they randomly accrue metals, or is there a very carefully balanced set point for how much of each metal there is in the cell? And that's where I'm going. I'm going to tell you this is a very tightly regulated ratio of all the different elements, and we see very few deviations until cells start going into very specific differentiation states and then take on new physiological roles. So we'll talk about how they sense metals. Then the question of one of chemical speciation. I think most of you recognize that the iron can be a +2 ion, it can be a +3 ion, it can be an aqueous complex with a small molecule, it can be bound tightly in an iron sulfur cluster in an enzyme. And so, the question of on each of these is how much is free or available. I'm going to show you how that can be a really important part of our thinking. And then if there's a lot of metals, then I'm going to try to convince you that from a cell biology point of view, or from a cellular point of view, these are hardly trace substances at all. But if there's so much of it, how does the right metal get to the right address in the cell? And we've made some progress on this, but there's a huge amount of distance to go. And then most of these questions are ones that a chemist can measure, that we can now, especially with extracting better and better physical methods from the physical and unities of physical sciences and instrumental methods, the synchrotrons, we can actually get down to counting how many metals are in a cell. But those are really kind of snapshots. The question is, can we look over time and look at a time sequence and see how, in the lifetime of the cell, these metals might flux between compartments, inside and outside the cell, and how those movements, those fluxes of metals, actually might perform critical switching roles in the cell physiology. So Karen Housen, when she was in my laboratory, developed a really clever way to think of the abundance of metals in cells. And there's a lot of ways to measure. This is one of them. This is an ICP-MS. The ions that come off it, you can see down to the part per trillion in sensitivity. There's a number of manufacturers. And what she did, she took all those numbers and then she divided the number of atoms by Avogadro's number and by the volume of the cell. And this happens to be a bacteria that's culture that was growing up in a minimal media, and where the metal concentrations were kept very low. These transition metals in here were kept at around 10 nanomolar. And in spite of that, the bacteria grew up to about 0.1 to 0.5 millimolar in terms of their total concentration. That's 4 orders of magnitude by which the iron was concentrated. Not too surprising, we know a lot about iron scattering systems. But it was remarkable to us that zinc was almost neck and neck, and in fact copper and manganese were always about an order of magnitude lower. As we've gone on and taken these results to the next stage, we've asked, was that something unique to bacteria, or do other cells do the same thing? And here's the numbers I showed you before, where we're just plotting the total amount of metal versus the total volume as a log plot. And what you see is that yeast, which are much bigger, and that mouse cells, which again are much larger, dog eggs, chicken eggs, etc. But there's this continuity. There's kind of a signature of these cells, most of which are undifferentiated, and that there's around 0.5 millimolar of zinc and of iron in the cells. And this still bores me today that there is such a high concentration. If I dissolve solutions of iron and zinc at those concentrations, you'd see it precipitate. The metals would react, and they want to fall out of solution. So the cells are spending a great deal of energy to concentrate. And there's this kind of a baseline that I want you to keep in mind as we go through the lecture. It's also remarkable that copper is about an order of magnitude less. For those of you that know the kind of the genetic lineage or the evolutionary lineage of these, I find this even more surprising because there's a vast difference in the number of types of metalloenzymes and metabolic pathways that are used in each of these organisms. Nonetheless, they seem to have evolved with the boundary condition of having a fixed amount of metal per cell as opposed to what particular enzymes needed. So this type of, I'll kind of throw up a green slide every now and then to show where we're taking some of these fundamental questions. And one thing that's becoming very useful is becoming an organic genotype of cells when they go bad. And so what we're doing here is measuring the metal content of a variety of different cells, some of which are tumorigenic and some of which are balanced counterparts that are not tumorigenic. And when we actually take all the elements of the profile, it creates an inorganic fingerprint, and that inorganic fingerprint allows us to sort out the ones that are tumorigenic. And we're not trying to do this for diagnostics. We're trying to do this to map differences in the physiology, what causes the cell to now turn off some of the regulatory boundary conditions and networks that keep it from becoming invasive and pathogenic. And so this is one direction we're going with the Systems of a Physical Science Oncology Cenogram from the National Cancer Institute. So what we are really excited about is that we can take those same cells and look at their transcriptomics and eventually their proteomics, and then look at the different genes that are controlling known metal concentrations in the cell. And right now we only know about what half the genes in any given organism do, and that's a generous prediction. But as we look at ones that are involved in metal transport and calcium and potassium, we're beginning to be able to correlate those genes that undergo changes in the cancerous phenotype and correlate that with the changing inorganic fingerprint. So this is work that's underway. I don't have a punchline for you, but I think that it's important to start realizing that there's an organic signature in all cells, and that they're relatively easy to measure, and that they might very well be telltale of the pathological state. More important to me is to see that they can be telltale of new types of signaling mechanisms and new receptors and pathways. Okay, so we talked about this. We described the inorganic signature of the cell as a metalome, and I would argue that there's an inorganic phenotype that's dependent upon the status of gene expression and the growth medium and the growth environment, and that's incredibly useful. But let's go on to how cells sense metals, and a family of proteins that are near and dear to my heart are ones that turn on and off gene expression, turn on and off the enzymes that regulate the expression of genes in response to metals. And the one I started my career on that John mentioned as a postdoc I worked on was a mercury sensor, where the switch was very simple. Bacteria don't like mercury. As soon as they sense it, they figure out a way to reduce it, and it evaporates from the cell. A very simple circuit. And from that, we were able to glean a variety of new ideas about how transcription works. I'll just give you a summary about a relative of our called QR. I'll also talk a little bit about ZIR. I want to point out that these were the list of genes back in 1993 that were known to encode metal sensors. What we now found is that there's really tens of thousands of these, often dozens per organism, that are play a critical role in balancing the inorganic physiology. In the case of QR, that's the small protein here. Its job is to sense changes of copper concentration in the cytosol of E. coli. And when it senses copper in the cell, it turns on a pump. The pump injects the copper, it turns on an oxidase, it oxidizes it, makes it less toxic. And if there's still copper coming in the cell, the next generation of protectors come in and move the copper all the way out of the cell, across the double membrane, across the outer membrane, and then yet again another set. So life has been set up, at least these microorganisms, to do all their copper chemistry out here in the cell envelope and try to keep the cytosol as free of copper as possible. So that's going to be an interesting parallel as we move up to multicellular organisms. What I want to do is just talk about this mechanism of a metal sensor that turns these genes off when there's no copper in the cytosol, and then turns them on and superactivates the transcription of those genes in the presence. And that protein is called QR, and the zinc sensing form, I'll show you in a minute, is known as VNTR. And we were just recently able to, this is actually published now, we recently solved the crystal structure of the protein bound to DNA when it's in the